So let's finally see an example of an uncountable set. And we will prove that it's uncountable using what's known as Cantor's diagonal argument. So Cantor is an old-timey dude who did a lot of work with infinite cardinalities. And this was his idea of how to prove that the real numbers are uncountable. And personally, I find it very beautiful because it's an amazing example of a very simple proof of a very wild idea, somehow. I mean, even thinking of the idea that there are different sizes of infinity is, was very astonishing to me when I first learned about this. But I hope you will find that this argument is quite simple, nonetheless, which is why I find it really beautiful. So, claim, the cardinality of the real numbers is strictly greater than the cardinality of the positive integers. Which is to say, the real numbers, R is uncountable. Oh, all right. How will we prove this? So what we want to show there is no bijection from the positive integers to the real numbers. So to be precise, let me not write this down, but I'll say it in words. To show that the cardinality of R is greater than the cardinality of the positive integers, we need to show that there is an injection, like so, but no bijection. And I think we can agree that there is an injection because this thing is a subset of this thing. Every positive integer is a real number. So that gives you an injection. So what we want to show is that there is no bijection. That's the second part. So let's say we have any map and we want to show that it's not a bijection. So how do we do this? Let's write it down. So the positive integers are countable, and we can use this to essentially write them all in a list, right? That's kind of what countable means, that you can write it down in a list. And let's write down where each element goes under our map, and I'm going to ignore the non-fractional part. And I'm just going to worry about the fractional part. So I'm drawing a box just to say that this can be whatever you want. I am just going to ignore it. But then after the box comes the decimal part, which I am just going to make up some digits. The point is that it doesn't matter what these digits are, as you will see. But I'm just going to write something down for concreteness. So let's get some random numbers in here. What are we doing? Okay, and the list goes on. So on, so on. Now, what we're going to do is we're going to write down a real number that is not in this list. And that will show that this map is not surjective and therefore not a bijection, right? So how do we write down a real number that is not in this list? Here's where the name diagonal argument comes from. So in the first row, let's look at the first decimal place. Okay, so we're going to write down a number. Let's just put a 0 before the decimal because we don't care about that part. And the first decimal place, I'm going to make it something different from this. So let me just make it the next bigger thing. I'll just keep that as a pattern. So the first decimal digit, I'm going to make it a 2. Then the second row, we look at the second decimal digit. And for our number that we're writing down, we make it something else. So again, let's make it the next one. And then the third row, we look at the third decimal digit and write down something different. And the fourth row, we look at the fourth decimal digit and write down something different. And we can continue this process until we get a real number defined by this decimal. And why is this number not in the list? We've constructed it perfectly so that it satisfies that property. Because it's not f of 1, because it differs from f of 1 in the first decimal place. It's not f of 2, because it differs from f of 2 in the second decimal place. It's not f of 3, because it differs from f of 3 in the third decimal place. And so on. So we've taken any function, any map, from the positive integers to the real numbers, and we've written down a number that is not in the image. So we conclude, so f is not surjective, and since f was arbitrary, there is no bijection from the positive integers to the real numbers. And this proves that the real numbers are uncountable. So in fact, let's give another example. Oh, I have space there. So in fact, the cardinality of the real numbers is equal to the cardinality of the power set of the positive integers. So you may remember, I think I mentioned this in lecture when we were defining the power set. I mentioned that the power set of a set is always strictly bigger than that set, even if that set is infinite. And this, now we know how to make sense of that. This is what we mean. So for example, the positive integers is our prototypical countable set, but the power set of the positive integers we now see is uncountable. And I want to introduce a theorem that you can use to prove this kind of thing that makes it a lot easier. Because this is actually, writing down a bijection between these sets is going to be an absolute nightmare. But fortunately, there's a better way. And it is called the Schroeder-Bernstein theorem. That's over there. And it says, it sounds quite simple, but as we'll explain, it is quite powerful. If the cardinality of A is less than or equal to cardinality of B, and the cardinality of B is less than or equal to cardinality of A, then the cardinalities are equal. But remember, when we're dealing with cardinalities of infinite sets, this is something that we know to be true about finite numbers. But for infinite sets, the way we've defined this, it's not obvious. It's saying that if there's an injection from A to B and an injection from B to A, then there exists a bijection between A and B. But if you have injections both ways, it's not at all clear how to construct a bijection. So let me very quickly give some idea about how to use this theorem to prove this fact. So what we need to do is give injections in both directions. So first, I'm going to give a bijection, actually, between the power set of the positive integers and the closed interval from 0 to 1. So I don't think I've used this bracket notation before. Probably familiar, but just to say it, this means real numbers, which are greater than or equal to 0 and less than or equal to 1. So let me be very sketchy in this proof. If you're interested, can go and work out the details later, but I'm not going to hold you to it. So the way this bijection works is translate a subset. Let me just write some subset and show you how it works. A subset like this corresponds to the real number represented by the binary decimal which has a 1 if your thing is in the subset, and a 0 if your thing is not in the subset. So it has a 1 in the nth decimal position exactly when n is an element of this subset. So this is indicating that 1 is in the subset. This is indicating that 2 is not in the subset. And so if we keep going down the line, 3 is in the subset, 4 is in the subset, 5 is not, 6 is, 7 is, 8 is not, etc. So that gives us a bijection like this that shows that these are the same cardinality. And now we will use the Schroeder-Bernstein theorem to show that this closed interval has the same cardinality as the real numbers. And the way we'll do that is by giving injections in both directions. So this one is clear. This closed interval is a subset of the real numbers. So we get an injection that way. And we can get an injection the other way by taking, for example, f of x equals 2 over pi arctan x. And maybe you have forgotten your inverse trig functions, but just to graph this, if this is -1 and this is +1, it looks something like this. So if you think very carefully about what this graph is telling you, it's telling you that this guy which is the domain, the real numbers, is getting mapped onto this guy, which is the interval from -1 to 1. Okay. So I'm realizing that I want 0 to 1 instead of -1 to 1. Oops, let's adjust this real fast. So what do I want? I want a function that looks like that. So instead of just taking this, I want to take I want to add 1 to shift it up, and then divide by 2 to switch it down. So 1/2 plus 1/pi arctan. Okay. So hopefully something like this works. Maybe I'll correct it in lecture notes if it doesn't. But basically, this gives an injection from the real numbers to the closed interval from 0 to 1. And we conclude that the cardinality of the power set of positive integers is equal to the cardinality of the closed interval 0 to 1. And that's equal to the cardinality of the real numbers. And we did not need to give an explicit bijection here, which is good, because doing that would be basically a huge nightmare.